Hello and welcome to this recorded e-learning on power estimation. My name is Frank Nelson. I'll be your instructor for this module. This module introduces Xilinx's power estimation capabilities. This module introduces some of the primary concepts that impact the quality of results a designer will get when planning for their FPGA's power consumption. This module also provides some recommendations about managing an FPGA's power consumption. If you are an experienced ASIC designer or new to FPGA design, this module will help you reduce your learning curve and get productive and anticipate your FPGA's power consumption sooner in the design cycle. The design practices and utilities we're going to discuss are designed to promote fast and efficient FPGA design construction with as little debugging as possible. Use of the power estimation tools and the recommendations for managing your FPGA's power consumption should give you more confidence about your ability to build a successful FPGA design. After completing this module, you should be able to list the three phases of the design cycle where power calculations can be performed. You should also be able to estimate power consumption by using the XPower Estimator spreadsheet. And you should also be able to estimate your power consumption by using the XPower software utility after you have built your design. Some customers are disappointed with their design results if they're building a system that is sensitive to power consumption. This module is going to show you how to use the primary utilities that Xilinx provides for power estimation. These utilities support for all Xilinx devices, including all of their FPGAs and CPLDs. Keep in mind that if you have power problems, there are still many possible solutions to the problem, including the addition of heat sinks, adding airflow, choosing a ceramic over a plastic package, etc. But our goal here is to give you the tools that will help you estimate your system's power consumption so you can anticipate any problems you might have as early in the design flow as possible. As you probably already know, as FPGAs get larger and faster, the power consumption goes up. This requires FPGA manufacturers to support higher performance and larger power requirements. This also has required designers and manufacturers alike to have package power limit concerns. The first generation of FPGAs was relatively small in size and slow in performance as compared to now. Power consumption was rarely exceeding the operating envelope of commonly available packages. However, given the density and performance levels of the new generation of FPGA devices, power consumption issues can no longer be ignored. Selecting the correct package, in particular, the ability to dissipate heat efficiently away from the silicon, is now also an important design issue. The Vertex family of FPGAs have gone one step further by incorporating thermal management on chip, allowing for active monitoring of the silicon via dedicated input pins. This is accomplished with the System Monitor block and is described in the Vertex 6 user guide. To get optimum speed, device utilization, and minimal power, customers need to plan on targeting as much of the FPGA's dedicated hardware resources as possible. This means that users not only have to plan on instantiating the proper resources, but sometimes have to look for creative ways in which to use the dedicated resources. For example, most customers would think to build a FIFO with a block RAM, but most would not consider building a finite state machine with block RAM. Very often, customers choose a device that has some dedicated resources left over. So to get the most out of the FPGA, users have to very often pack the most into the FPGA for the same benefit of trying to reduce their power consumption. As you know, higher density devices require more power, and this leads to higher junction temperatures. Package thermal limits exist for all Xilinx devices, and it is important for you to anticipate your FPGA's junction temperature as early as possible. This is especially important since you will probably have to choose a package for your device early in the design flow, and changing this package can be very costly. To help you with this, you can use either the Xilinx Power Estimator spreadsheet or use the XPower Analyzer. The spreadsheet is the earliest possible form of power estimation, since it only requires you to have a rough estimate of your device utilization and an estimate of your activity rates. The XPower Analyzer will require you to have already built, synthesized, and implemented your design for power estimation to occur. But the XPower Analyzer estimate will be a more accurate estimate than that available from the Estimator spreadsheet. And as you know, estimating your FPGA's junction temperature will determine whether you can choose a less expensive packaging option. But this choice will also determine if your design can run at your system performance objectives, design density, use the package options you want, and of course operate reliably. Estimating power consumption is a complex calculation. It has two factors: quiescent power, which is static power used to turn on the device, and dynamic power, which is dependent on the switching frequency, design activity, that is the percentage of toggle rate, and is different for each resource in the FPGA. Taking both the static and dynamic power consumption for each individual resource in the FPGA together suddenly makes power estimation a daunting challenge. This is why the Power Estimator spreadsheet and XPower analyzer are so helpful, because they are so detailed about the overall FPGA's power consumption. Power calculations can be performed at three distinct phases of the design cycle. At the concept phase, a rough estimate of the power can be calculated based on estimates of logic capacity and an estimate of activity rates. This is done with the Xilinx Power Estimator spreadsheet. It can also be done during the design phase. In this case, power can be calculated more accurately based on detailed information about how the design is implemented in the FPGA. And this is, of course, done because the design has been coded, synthesized, and even completely placed and routed or implemented with the ISE tools. Thus, all of the logic resources that are actually going to be used to construct your design, including the routing, clocking, and dedicated hardware resources, are all known. And this estimate is done with the XPower analyzer. Lastly, during the system integration phase, power is calculated in a lab environment using the actual instrumentation. Of course, that's really the final say on your power consumption. But accurate power calculation at an early stage in the design cycle will result in fewer problems later. Well, as I mentioned earlier, activity rates are important for making your estimate as accurate as possible, and are also the toughest for you to estimate on your own. You'll have to estimate your own activity rates for each element in your design. This may seem difficult, but you can assign a default activity rate, which is what most people do. But the more time you spend estimating the activity rates, especially for your high power consuming components, the more accurate your estimate will be. While clocks and inputs have an absolute frequency associated with them, synchronous nets and logic will need an activity rate associated with them as well. An activity rate is a percentage of the time on each clock edge you expect the component to toggle. That means if you expect it to toggle on every clock, like the least significant bit of a counter, then its activity rate will be about 100%. Likewise, the most significant bit of a 16-bit counter won't toggle much at all and can be ignored. Now, this will vary by design, but only you know your design well enough to estimate your system activity rates. Just don't ignore the activity rates and only work with the default activity rates. Try to spend some time estimating your activity rates, at least on a component basis. That way your estimate is as accurate as it possibly can be. The Power Estimator is a spreadsheet that allows you to enter design data into boxes, that is, your activity rates, number of resources, and the source clock frequency, and then quickly generate a power estimate for your design. This spreadsheet segments each design by resource type. For each resource shown will have its own spreadsheet. Now, this is a good time to remind you that the power consumption of each resource is significantly different. In fact, ideally, you'll target the dedicated hardware resources as much as possible, rather than use just the CLB logic resources. Now, this is because the dedicated hardware is optimized for minimal power consumption as well as high speed. So be sure you're getting the correct hardware resources inferred by your synthesis tool, since it will choose which resource to map to based on your HDL coding style and any instantiations you place in your design. To help you with that, we have several free recorded e-learning modules at support.xilinx.com which explain how to optimize your code and optimize your design for your device architecture. Writing good HDL is of course important because it is used by the synthesis tool to infer the resources. Since there is very often more than one way to code effectively for the same functionality, it is important to understand the differences between the two, and of course use your schematic viewer to verify that you're getting the resources you expect. This is compounded by the fact that often a poorly coded piece of logic creates a timing-critical path for a designer to resolve later on, and often designers waste a great deal of time resynthesizing and repeating place and route in hopes of meeting a timing objective. Now, this slide is trying to highlight some of the benefits of the dedicated hardware resources that exist. The most useful is the DSP slice and the block RAM resources. Besides using less power and saving FPGA resources, that is, the primary resources, LUTs and registers, using the dedicated hardware makes it easier to estimate your timing, and that's because the architecture delays of the dedicated hardware are known or fixed before place and route. Unlike data paths that are mapped to LUTs and registers, these dedicated paths that include the dedicated resources effectively only have a programmable routing to the resources. The actual logic resources, again, are fixed in the silicon. Another reason to use the dedicated resources is that compared to soft implementation, that is one that is synthesized for LUTs and registers, the speed by using the dedicated resources is significantly higher. So be sure to use as much of the dedicated hardware resources as your design needs and as you can, and if you think you may be running out of primary FPGA resources, that's LUTs and registers again, consider implementing more of your design in leftover dedicated hardware. Finally, we wanted to point out to you that the Xilinx Power Estimator spreadsheet that we're about to cover must be downloaded from our website. It is not installed with the ISC software, and this can be found by going to the Power Solutions webpage, as you can see the directions here on this slide. This page also has numerous resources on how to manage your FPGA system power consumption. So if you have any questions about power consumption, I really encourage you to start here. First of all, the Power Estimator is just an Excel spreadsheet that has your device's thermal information already built in. When you open the Power Estimator, you'll see a summary sheet, and in this case, we had to segment what you see into 2 slides so you can actually look at some of the details. Now, this tool will use a default activity rate of 12.5% and uses standard operating conditions, but all these values can be modified by the user. You simply enter new values in each white box, and the new power estimates will automatically show up in the gray boxes. Note that at the bottom of the GUI there are tabs for each FPGA resource type, so before you can see the total power consumption, you'll have to go to each resource page and enter the amount of those resources, number of block RAMs, number of LUTs, number of registers, their frequency, and the activity rate for each resource. And this is necessary to give you the best estimate. Then the new power estimate information will be updated on that summary page. So in this slide, we can see, first of all, on the settings page that there are white boxes for us to customize. In this case, the settings page includes device family information and a chosen device density, as well as environment information, such as are you using any sort of airflow in your environment, do you have a heat sink they're using, what's the ambient temperature. And then, of course, the on-chip power will break the estimated power consumption. Now, that is, after you've entered your white boxes, it will show you your power consumption based on your device resources. The power supply page includes information about the necessary voltages for your device family and your design and what it will require. In this case, that includes core voltage, I/O voltages, as well as any other voltages based on your I/O or any dedicated silicon you're using that may be required for your design based on how you describe what resources you're going to use for your design. It also segments power by logic resources and provides an expected junction temperature, which is located on the summary area. It even breaks down power consumption by quiescent and dynamic power. That way you can choose to focus on which resources so that you can perhaps reduce your power consumption. It also segments a summary into device resources, calculates an expected power consumption, and provides a thermal margin. This slide shows you how your clock, logic, and I/O resources can be customized. The clock tree power consumption is dependent on the distributed clock frequency, fan-out, and use of the global buffer. That is, specifically if the clock buffer enable is used. The logic power estimate requires clock frequency, number of logic resources by type. In this case, that could be a LUT, shift register LUT, distributed RAM, and flip-flop that is associated with each clock domain. This will also require you to estimate the average activity rate, shown here as a toggle rate. It also asks for the average fan-out for each resource. This allows high fan-out nets to be estimated as well. The I/O power requires the same kind of information, except it also needs your output loading and some details about how each IOB will be configured. That is, what I/O standard is used, whether the output enables used, data rate, SerDes functionality, I/O delay, and of course slew rate. As you will see, I/O power consumption is a considerable factor in your overall system power consumption. This slide shows you how your block RAM, DSP slice, and your clock management resources, that is the MMCM resources, can be customized for the Power Estimator. The block RAM and DSP slice resources need a little more information that is specific to those resources than, say, the CLB resources needed. The clock manager, or MMCMs, need specific information about how each derived clock signal is going to be made. You may recall that each has the ability to derive up to 6 clocks and will be dependent on how each clock output was derived and its frequency. The Power Estimator spreadsheet also includes some graphing functionality that allows you to see how your FPGA's power is being consumed. In this case, our little design is mainly consuming static power. As you can see from the upper left-hand corner graph, the bar chart for leakage is by far the largest. Well, that's because the design is very, very small, not even a fair test case. But it was all I had, and I just wanted to demonstrate this utility. This chart is probably the most helpful because it easily allows you to determine which device resources are using the most power. This is helpful in case you decide you have a power problem. Then you can determine where your power is going and perhaps consider making some design changes, such as porting logic to dedicated hardware or choosing different I/O standards on some I/O pins. We will talk more about what options you have later on. Further to the right, we see a chart for power versus core voltage behavior that is described. This will give you some idea as to whether increasing your core voltage, which in turn improves your system speed, can be tolerated thermally. On the bottom, the power variance for core voltage and temperature for your chosen device is shown. This allows you to see the impact of ambient temperature and core voltage on your device. And on the bottom right, the current versus your junction temperature is also shown. The XPower Analyzer is another power estimation utility. The difference is that it requires the design to be built, synthesized, and implemented. That means that this estimate is even more accurate than that produced by the Power Estimator spreadsheet. However, you will still need to supply the same information about the performance of the design, such as clock frequencies, activity rates, capacitive loading, power supply information, and ambient temperature. While this same information can be loaded manually, it also can be read in from a VCD file, which is a detailed design activity data resource from your simulation tool. A value change dump, or VCD file, is created by a simulation tool, such as Mentor Graphics ModelSim, for example. The VCD file contains information about signal or variable value changes. The VCD can be read by the Xilinx XPower Analyzer to provide accurate power estimation. Note that in order for the XPower Analyzer to match instance and net names from the VCD file to items in the NCD, that is your implement result, the VCD file must be from a post place and route simulation. The XPower Analyzer is located in the IC tools beneath the place and route. From here, you can start the utility or load the VCD files or run the XPower Analyzer from the command line. To load a VCD file, you right-click on the XPower Analyzer to open the process properties and browse to the simulation output file location. The XPower Analyzer, like the spreadsheet, is both a report generator and a utility for entering design information in one. So as you browse the GUIs, note that the non-gray windows are for either reporting power information to the user or entering design environment information by the user. And as you enter or update new data, you will need to click on the Update Power Analysis button on the horizontal toolbar. The net result, like the XPower Estimator, is a junction temperature, and like that estimation, this utility lets you break your power consumption into logic type. The Report Navigator in the left-hand area of the GUI allows for quick navigation to various resources. This includes specifying thermal information, voltage source information, settings, and logic type. The Report Navigator allows you to jump to various pages of the utility to enter component information. The Thermal Information tab allows you to enter an ambient temperature, custom theta JA based on the package type you've chosen, specify airflow, heatsink type, board layers, and determine the maximum ambient temperature for your device and the estimated junction temperature. The Voltage Source tab allows you to specify your anticipated core and I/O voltages you plan to provide to your system. The Settings tab allows you to specify a different grade device, whether that is an automotive, commercial, or industrial grade, but also define your output loading and all of your system toggle rates. The By Type area allows you to specify for specific toggle rates, clock frequencies, and other characteristics for each resource type in your design as well. The Advanced Report provides you a simple text file that contains the same information you can find from the XPower Analyzer GUI. But this report does include a bit more detail and some what-if analysis. This report will allow you to quickly determine your package power limits and the estimated junction temperature for 250, 500, and 750 linear feet per minute airflows. This text report also has a power improvement guide to offer you some suggestions on managing your power. At this point, you're probably wondering what you could possibly do to improve your FPGA design's power consumption. Well, there are a lot of things, and frankly, there is no way I can deal with all of the possible options in just one slide. First of all, you need to keep in mind that your knowledge of your FPGA's power-saving FPGA resources is important, and this can only be done by reviewing your device user guide and/or datasheet. Now, keep in mind that close attention to detail will provide you with numerous options that can help you save power from within the silicon. The problem is that many of these features may degenerate your speed. For example, going from fast to slow slew rate will save power, but will hurt your I/O performance. So, you're going to need to try to determine which parts of your design are using the most power. In this case, the XPower Estimator spreadsheet can be very helpful for that purpose. And if you can, this will enable you to try to retarget CLB resources to dedicated hardware. Now, you should also read the Power Improvement Guide section of the Advanced Power Report. You should also evaluate your activity rates and make sure they're as accurate as possible so the reporting is most accurate. But there's still many more things you can do. You should evaluate your synthesis options. Enable settings which favor power optimization or area minimization. You can experiment with synthesis options which affect the design size, the number of signals, as well as the activity rate. Consider loosening the constraints when possible to limit the number of logic replications. That, of course, would affect your design size. Change the mapping threshold or add constraints to implement more of your logic into dedicated and lower power hardware blocks, such as block RAM or DSP slices. You should also evaluate the use of the implementation tools. Enable the implementation tool settings which will favor power optimization. Experiment with the map and PAR, that is the place and route options, which may affect power, such as options which modify the input netlist, packing, placement, or routing resources used. Loosen the constraints when possible to get a more tightly packed design. Also, consider altering your HDL source code. Ensure the design code is efficiently written for the targeted device. Code reused from previous or different device generations may be synthesized suboptimally and need you to be recoded. Minimize the number of control sets. Remove asynchronous resets, which are typically not necessary in FPGAs. Now, we discussed the use of control signals and control sets in the Spartan 6 and Vertex 6 HDL coding recorded e-learnings. You may need to reduce excess static power as well. There's very little you can do with the implementation tools to lower your static power. You'll most likely need to change the design code or the IO interface to do so. You also can adjust external environment properties that are affecting your device power. At this stage in the development cycle of the printed circuit board is already being designed, and the voltage regulators, cooling devices, and other device environment properties are set, so changes you can make in this area are often restricted. It may, however, be possible to supply more cooling or lower the supplied voltages. So these are just a few of the big ideas that can be used to help you resolve a power problem. Now let's wrap up this module with a brief summary. Power calculations can be performed at three distinct phases of the design cycle. At the concept phase, they can be estimated with the Power Estimator spreadsheet. During the design phase, they can be estimated with the XPower analyzer, and of course this is after the design's been coded, synthesized, and implemented. So it's a better power estimation than the concept phase, which is the use of the Power Estimator spreadsheet. Also during the system integration phase, when we can actually use lab equipment, that of course is going to be the actual power consumption on my expected system, and that's going to be the best result, but of course that's latest in the design cycle. Accurate power calculations at an early stage in the design cycle will result in fewer problems later. The Power Estimator spreadsheet and the XPower analyzer can be used for estimating the power consumption and the junction temperature of all Xilinx FPGAs and CPLD devices. The Power Estimator and the XPower analyzer use activity rates to calculate the total average power consumption. Now there are some very useful resources available to you. First of all, the Command Line Tool User Guide has an XPower chapter, and this will describe in a little more detail the XPower's information, its utility functionality. There's an online help for the XPower GUI. And I want to point you to, again, that Xilinx Power Solutions webpage. And here are the instructions to get there by going to support.xilinx.com. From here you can get the XPower Estimator spreadsheets for all different Xilinx FPGA families. And there's a couple of other documents you might want to look at. First of all, the 7 steps to worst case power estimation really walks you through the power analyzer and the power estimator and helps you understand how the settings you make there are going to be best suit for a worst case power estimation. So it's a really helpful little document to help you understand how to use those utilities. There's also a Spartan 6 Power Management User Guide you should have a look at. And there's also a document that kind of explains the power consumption at the 40 and 45 nanometer silicons. There are also a number of application notes that you can go find, including XApp 158 on powering Xilinx FPGAs. So again, one of the other considerations is after you've determined your power consumption, you still have to apply the necessary power sources to your FPGA to get it to work properly. And lastly, as we mentioned here, the Xilinx education page, we have some further RELs on power consumption as well as on various topics. So if you want to learn more about what other courses we offer or other RELs, go to this location. Again, my name is Frank Nelson. You've been listening to the Power Estimation Recorded Learning Module. Again, thanks for your attention, thanks for listening, and thanks for your business.